kinetic consideration of crystallization and specifically discuss the crystallization rate. So we know, again, the process of crystallization depends on both kinetics and thermodynamics. So at low temperatures, so when my temperature is very, very low, I'm going to prefer nucleation. And when my temperature is high, and we're going to get into this in a bit, I'm going to prefer growth. So at low temperatures, our entropic contribution, our delta S, is going to be, this magnitude is going to be small. So our system is going to want to lower the free energy of our system by adopting a more ordered morphology, i.e. form this lamella structure and create crystalline structures. So that's how we're going to minimize our free energy. But as our delta T decreases, or as our undercooling increases, fluctuations in transport, specifically diffusion, which we know to be erroneous with respect to temperature, that is going to decrease as temperature decreases, or as our temperature decreases, our undercooling increases. Your diffusion decreases as well. So that is going to hurt the ability of our ordered regions to grow. So there's going to be this really delicate balance between the thermodynamic driving force, i.e. to nucleate a crystal at low temperatures versus growing that crystal at high temperatures. So the rate of crystallization will be defined at which the sample becomes, the rate at which a sample will become crystalline. So that is going to occur. We're going to maximize our crystallization rate, so our crystallization as a function of delta T at some magic undercooling that's intermediate. Because at very, very high undercooling, we're going to push for nucleation. At very, very low undercooling, we're going to push for growth. And we're going to see at some intermediate undercooling, we're going to maximize that crystallization rate. I posted some videos from Engineering 45 just to kind of remind you about this nucleation growth in case you haven't seen it previously. So we need to nucleate spherulites and then grow those existing spherulites in order to kind of completely crystallize our system. So you can imagine we have two scenarios. When my delta T undercooling is really, really, really high, I can form nuclei everywhere. But the problem is the temperature is so low that in order to grow the nuclei, the polymers aren't kind of diffusing and growing. Basically, these nuclei can't grow because the polymers, it takes forever for them to fuse in. If I have a system here where my delta T is very, very, very low, my undercooling is low, i.e. my temperature is high, I could, of course, I'm only going to have a couple of nuclei. Now, any of these nuclei, these polymers are going to be diffusing and these guys could grow, but again, there's so few nuclei that it's going to take forever for my system to be fully crystalline. So I need to have this Goldilocks intermediate, undercooling and temperature so that I can maximize my number of nuclei and so that those nuclei can grow via diffusion. So that's how we're going to maximize the crystallization rate of our system. So let's go ahead and look at this two-step process for nucleation and growth. So it's basically identical to nucleation growth of small crystals, again, like you've seen in some other YouTube videos that I posted for Engineering 45, so I would definitely suggest watching those. So nucleation, basically a crystal forms spontaneously due to some thermal fluctuation. So your polymer spaghetti, those chains are flapping, and at some point they start to fold, and due to that thermal fluctuation, they start to form spontaneously this nuclei of a crystal. So the initial nucleus, elongated, folds onto itself or a neighbor, and that's how your initial nucleus will form. So that initial nucleus, you can kind of just idealize it as like a particle. That particle, that nuclei, is going to have some surface area and volume. Surface area is going to have some surface energy. Creating surfaces is bad. Why? Because you have this ordered surface in contact. So inside here at that surface, we have order. Beyond that, you have just polymer chains that are disordered. This disordered surface is not energetically favorable. Creating surfaces is never energetically favorable. It costs energy. So there's going to be unfavorable interactions between the surface and the bulk. But the nucleus is stabilized because inside, i.e. in the volume, you have these nice, enthalpic interactions where it's ordered, and those van der Waals interactions or H bonds or these non-specific intermolecular interactions, they're going to stabilize that crystal and lower your energy. So stabilized by favorable interactions in the volume of the crystal. So to form a stable nuclei, we need, it depends a lot on the surface area to volume ratio. So we need to maximize our volume and minimize our surface. So when my nuclei is really, really, really small, I've just formed like that single chain fold, the surface to volume ratio is really, really high. So that is going to oppose the formation of a nuclei. But as my nucleus gets bigger and bigger and bigger, that surface area to volume ratio is going to decrease. And at a certain critical size, the free energy change achieves a maximum. And then beyond that, you're decreasing your free energy. So let's go ahead and look at that plot right now. So this is essentially, and again, you'll see this in the, so at low, again, you can see this, you're going to have an interfacial term, as we saw in, Engineering 45, interfacial term that opposes the growth of a nuclei. So that's positive free energy. Volumetric, which is negative free energy. So we know that at very, very low values, my R squared is going to be, for low values of R, and R is really, really small, less than 1, R squared is going to be greater than R cubed. But as we start to grow, our delta G here, we hit a maximum, and we know our reaction is spontaneous when the derivative delta G with respect to some variable R is less than 0, and that slope is negative here. Our delta G is decreasing, so now we're going to grow. But we have to basically, until we hit this critical radius R, the nucleus is not stable. It will not want to grow. So here we want to grow, here we want to shrink. And why is that? It's because this competition between surface area increases my delta G and my volume decreases my delta G. So let's go back to the notes. So let's go back here. So at critical size, we're going to be, the system is going to want to grow. So once you have that critical size nucleus, growth is thermodynamically favorable because that's going to reduce the free energy of our system. And again, you could kind of think of that delta G as a function of R. You can think of that equation, this as like your free energy barrier. So this is like your delta G of nucleation. So there's some energy barrier to form this nuclear size. Because again, it's going to depend on these fluctuations in the system, formation of a cluster. So we need to overcome this energy barrier. This is your R star, your R critical. And beyond this, then our system is just going to proceed to grow. We're going to grow those crystals. Crystal size, again, the elongation of a chain. So again, it's a little bit different from polymers or material science when we're just looking at a solid kind of nuclei. Here we're looking at basically a nuclei like a spherulite. So this critical radius is almost like your lamellar chain thickness. Anyways, but we know that elongation opposed, again, as this increase in entropy. So high temperatures, very, very hard to do. This is very, very high, high temperatures. Why? Because we know that T delta S, we want to maximize that conformational entropy. So that is going to be difficult to do that, to spontaneously elongate that chain. So as temperature drops, that nucleation is going to become much, much easier. So the key aspect, the key thing to kind of see, and we'll see this, actually we derived this last time, is that your delta G of your volume or your nucleation is going to be proportional to this delta T, your undercooling. So nucleation is favored at lower temperatures. We can kind of see that in this equation right here. This is effectively, we see it scales, and we actually showed it last time, that your delta GV or your lamellar thickness scales directly with your undercooling. And we actually see right here, this is your surface, and this is what's fighting against it, but here your delta GV scales with the amount of undercooling. So that rate of nucleation, so my nucleation rate, as we're going to see in a bit here, that nucleation rate is going to scale as a function of that nucleation. So the nucleation rate is going to be this exponential minus G over KT. It's going to be some Arrhenius term. And that delta G term is going to be a function of this minus delta GV, which we dealt with last time, plus that delta GS. So that's going to be the competition. And at low temperatures, at high undercooling, we're going to want to nucleate. So next time we'll get into growth, which is going to occur at low amounts of undercooling and high temperatures. So I'll see you all next time. Thanks. Bye.